Hello, everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to continue with the chapter Atomic Structure, and we will particularly be talking about the discovery of electron. Now, when I talk about the electron, which is a subatomic particle, if you remember in the previous lecture, that was the first lecture when we were talking about the introduction part, we just introduced that there are particles which are smaller than even the atom, and these are called subatomic particles. These include electron, proton, and neutron. We will be talking in detail about all these three subatomic particles, and here in this lecture, we will be focusing on the electron. The first thing that we are going to talk about is the discovery of electron, that how and what experiments did actually lead the scientists to discover the electron. Before we begin, a piece of information for you. You can use the coupon codes Mission JEE or Mission NEET while you enroll at First Online University for Mission JEE or NEET. Let us start with discovery of electron. Now, before going into the details of how the electron was discovered, there is a basic rule that we need to keep in mind. And that basic rule is like charges repel each other and unlike or opposite charges attract each other. So, finally, let us look at the discovery of electron. So, Michael Faraday was the scientist who was studying the discharge of electricity, okay, how electricity was being generated in partially evacuated tubes, which were known as the cathode ray discharge tubes, okay, also known as the CRD tubes. So what he was doing was that this particular scientist, Michael Faraday, was actually making use of evacuated tubes, means which had actually vacuum in them, which were known as cathode ray discharge tubes or CRD tubes. And he was studying the discharge of electricity. What happened was that the electrical discharge through gases was observed only at very low pressures and very high voltages. The pressure of different gases was adjusted through vacuum pump by their evacuation. So whatever gas we were taking, by evacuating some of the gas, we were able to adjust the pressure inside the cathode ray discharge tube. So this was the entire setup where you had a cathode and an anode, and then there was this vacuum pump and high voltage. So vacuum pump was required to lower the pressure and high voltage was again required for the purpose. So this is how a cathode ray discharge tube looks like. A cathode ray tube is basically made of glass which contains two thin pieces of metal electrodes which are sealed in it. Now, when we applied sufficiently high voltage across these electrodes, so when voltage or potential is applied across these electrodes, the current will start flowing, and because of the flow of the current, there is going to be a stream of particles also moving in the tube from the negative electrode to the positive electrode, that is from cathode to anode. The particles are going to move. These are called the cathode rays or cathode ray particles. Okay, the particles that are moving from the cathode to the anode, these are called cathode rays or cathode ray particles. Because they are emanating or starting or being generated from the cathode, we call them as cathode ray particles. Now, in the absence of electric field or magnetic field, the cathode rays or cathode ray particles are going to travel in straight lines. It is only in the presence of electric field or magnetic field that they are going to change their paths. So what is happening is, this is where we have the negatively charged cathode towards the left and the positively charged anode towards the right. And from the vacuum pump, we are adjusting the pressure. And when we apply high voltage, what we see is that here on the fluorescent screen which is present. So this is the fluorescent screen, okay, which is present just before the anode. On application of high voltage, and there is a perforated anode, okay. Now what will happen is, on application of anode, the particles are going to move in a straight line from cathode towards the anode, and they're going to pass through this perforated, means anode, which contains small holes, and it is going to produce a scintillation on the this screen that we have. So cathode rays are going to cathode rays tube, discharge tube with a perforated anode is going to function in this way. So the next thing is that when the flow of current takes place from the anode to the cathode, it can be checked by making holes in the anode and the coating behind the tube, okay, behind the anode with a phosphorescent material, and that phosphorescent material is basically that when these cathode ray particles are going to strike this phosphorescent screen through the perforated anode, they are going to produce a scintillation. Now what is a scintillation? Scintillation is basically a flash of light that is produced when any phosphorescent material is going to be hit by such high energy particle. So the commonly used phosphorescent material is zinc sulfide. So what happens is that these rays, once they pass through the anode, are going to strike the zinc sulfide screen. As a result, a bright spot is going to develop, which is called scintillation, and that's the same principle that follows in the television sets also. Okay. Now, what happens is when there is no electric or magnetic field present, we know that the cathode rays or cathode ray particles are going to travel in straight lines. In the presence of electric field or magnetic field, however, the behavior of these rays is going to be similar to that of negatively charged particles called electrons. So, the characteristics of cathode rays is that that means the electrons, they do not depend upon the material of the electrode and the nature of the gas that is present in the cathode ray tube. Whatever material of electrodes you take, whatever gas you take, the cathode ray particles or electrons. Now here, do remember why am I using these two words interchangeably, that is cathode ray particles and electrons. That is because in the presence of electric or magnetic field, it is these cathode ray particles only which behave as electrons. So whatever material of the electrode you take, whatever nature of the gas you take, these electrons are not going to depend on these two factors. The basic constituents of all the atoms are electrons. Cathode rays are basically made up of particles that rotate light. Okay, so that's basically because they are able to rotate a light frictionless paddle wheel. You can actually just leave this point as of now. It's a something related with a tool that is used in physics, an instrument that is used in physics. Cathode rays are going to come out at right angles to the surface of the cathode. Okay, so it's like this is the surface of the cathode. The cathode rays are going to come like this out. Okay, it's like this. So at 90-degree angle is what we have, the cathode rays coming out from the surface of the cathode, and the direction of emission, the direction in which they are going to move towards the anode, will not depend on the position of the anode. It's not like the anode is pulling them. They are going to move in a straight line because it's the absence of electric field or magnetic field. They are not formed in the evacuated discharge tube. Remember, cathode rays basically are going to ionize the gases that are present in this glass tube, indicating or proving that they are charged. It's like only the charged particles can ionize or break other molecules into charged particles. So the next thing is we need to now talk about, so this is how we have seen that the experiment where the cathode ray discharge tube, which is a glass tube consisting of a cathode. So I'm just summarizing it for you. We have a glass tube which has the cathode and the anode, and a high voltage is going to be applied to it so that the cathode ray particles are going to be released from the cathode, move towards the anode. In the presence of electric or magnetic field, these are going to behave as electrons. So this led to the discovery of electrons. How it was proved that cathode ray particles or electrons were released was because when they passed through the perforated anode wall and went on to the zinc sulfide, which was the phosphorescent screen, they produced a bright spot or scintillation effect that actually showed that these particles collided with the zinc sulfide sheet and produced a bright spot. So this led to the discovery of electrons. Now the next thing that we need to talk about is that since electron has a negative charge, so it carries a charge, And since it is a particle, it will be associated with some mass. We will now be talking about the charge by mass ratio of the electron. So that's also represented by E by M. Now this concept will first study about how, some basic history also. So J.J. Thomson was the scientist who in 1897 measured the ratio of electric charge, that is E, to the mass of the electron, which is given by ME, by using cathode ray tube and applying electric and magnetic fields that were mutually perpendicular to each other, as well as to the path of the electrons. Now, I just previously mentioned that the path of the electrons was perpendicular or at right angles to the surface of the cathode. So imagine if this is the surface of the cathode and the particles are going to come in this way, the electric field is going to be in this way, and the magnetic field is going to be in the z direction. So all three of them are going to be mutually perpendicular to each other. And since in the presence of electric or magnetic fields, the cathode ray particles are going to behave as electrons, therefore, we could actually study the electrons through this experiment. Now, the apparatus to determine the charge to mass ratio of an electron is going to be looked somewhat like this. So what it was is, you have the anode that is being highlighted here. Then you also have the cathode, which has been shown here. This is brownish reddish thing is the magnetic field, and this is the fluorescent screen where ABC are written. This is the electric field. This is the electric field, this is the magnetic field, which are mutually perpendicular to each other. Now this was the movement of the cathode ray particles from the cathode towards the anode, and the path you can see of the cathode ray particles is mutually perpendicular to the directions of the electric and magnetic fields. This went on to the phosphorescent screen, passing through these three pores A, B, C. So next thing was the amount of deviation of the particles from their path in the presence of electric and magnetic field depends on number one, the magnitude of the negative charge. Okay, so higher the charge, more is going to be the deviation. So what we say here is that greater the negative charge, greater is the interaction with the electric or magnetic field, and greater will be the deflection. The second was the mass of the particle. So mass of the particle, lighter the particle, higher was the deflection, because when something is lighter, you are able to push it anywhere, put it anywhere, but something which is heavier is not easy to lift and keep somewhere else. So please remember through this mnemonic. Okay, the amount of deviation, okay, also depends on the strength of electric or magnetic field that is being used. The deflection of the electrons from their original path is going to increase with the increase in voltage across the electrode or the strength of the electrons. The moment we are going to increase the voltage or the moment we are going to increase the strength of the electrons, one is the same thing. We will have greater deflection of electrons from their original path. Now, when only electric field is applied and no magnetic field is applied, then the electrons are going to deviate from their path and hit the kit. So if you remember, we had A, B, and C spots on the phosphorescent screen. So there, when we have only the electric field applied, which was coming from upward, then the cathode ray particles are going to deviate from their path at point A. So they'll hit the cathode ray tube at point A, as it has been shown in this figure. By balancing both electric and magnetic fields, the path made will be a straight line. That is, it is going to hit the zinc sulfide screen at point B. And when only the magnetic field, because magnetic field is towards the downward. So it's going by simple logic. A field that is being applied from upwards will pull the electron towards itself and it will go in that direction. And if there is a field coming from downwards and this is going to be interacting with the electron, then it is going to make the electron deviate from its path towards the downward side. Okay, so that is, it is going to hit the cathode ray tube towards the point C. So now, by carrying out accurate measurements on the amount of the deflections that were taking place or that were observed by the electrons, on the electric and magnetic field strength, J.J. Thomson was actually able to determine the charge to mass ratio. Do not forget that our basic aim remains the same. We are going to be talking about the charge to mass ratio only. This was just an experiment to tell you how he was able to actually use this deflection process to predict the charge to mass ratio. So charge by mass is basically specific charge, that is charge per unit mass. We know the value of charge by mass ratio is basically 1.75 into 10 raised to power 11 coulombs per kg. Remember, this is an important value. E is the charge of the electron, which is 1.602 into 10 raised to power minus 19 coulombs, and Me, which is the mass of the electron, is 9.11 into 10 raised to power minus 31 kg. You put the value E by M, calculate if the answer is right or not. That's the standard value only. All you need to do is to remember all these three values. So just in case if you forget E by M ratio, you should know E and you should know M anyhow, and then you'll be able to produce this answer by yourself. Next is the charge on the electron. Now, when I talk about the charge on the electron, the experiment that was carried out to determine what was the amount of charge on the electron was actually carried out by the scientist R.A. Millikan. So he actually devised a method which is known as the oil drop experiment. So in this experiment, he actually saw the dropping of the oil drop, okay, and that he used as a measure to determine the charge of electrons. So this was the experiment. If you look at the setup, so there was oil that was being sprayed into fine droplets, and then there was this pinhole. Okay, so this is where the oil is being sprayed into fine droplets, and then there is a pinhole here. So the moment, and this plate was positively charged, this plate was negatively charged, and then there was another hole where the X-rays were entering in order to reduce the charge on the oil droplets. Okay, so from this hole, the oil droplets were falling down, and this X-ray tube actually gave them a charge. So that now these charged oil droplets were falling onto this plate, and these two plates were brass plates, were also electrically charged. And here was the telescopic eyepiece through which we could observe what was happening inside the entire setup. So this is my atomizer that is going to produce fine droplets. Now, what was this Mulliken oil drop experiment? What happened was that when this positively charged plate, okay, was placed above a negatively charged plate, and there was a pinhole, that is a small hole made onto it. This was also connected to another hole from which the X-ray was entering through the source, and through this atomizer, the oil drops were actually falling onto this positively charged plate, moving towards the pinhole. And when we observed it through this telescope, we saw that these drops, as soon as they fell from the pin, that is the small hole, they were made charged by the X-ray from the source. This is the oil droplet under observation. So once the experiment happened. So it was like the oil droplets were produced in the form of mist by the atomizer, and they were allowed to pass through a small hole which was there in the upper plate, which was positively charged, of the electrical condenser, and the downward motion of the oil droplets was observed through the telescope with a micrometer eyepiece. Now, by measuring the rate of fall of these droplets, the rate at which these droplets were falling, the mass of the droplets were actually determined. This air chamber was ionized by passing a beam of X-rays through it from the right-hand side that was coming. The electrical charge on the oil droplets is acquired by the collision with the gaseous ions. Now, because we know that in this entire chamber, there is gas that is present, which was ionized. So because of these gaseous ions, the collisions happened between this oil droplet and these gaseous ions that actually led to the development of charge on these oil droplets. The fall of these charged oil droplets can be retarded or accelerated, or it could be made stationary, depending upon what was the charge on the oil droplets. So by making the oil droplets fall, we were finding out the mass of the oil droplet, but the rate at which it was falling could be either increased or decreased or made stationary, by changing the charge on the oil droplet along with the polarity and the strength of the voltage that was being applied onto the plate. Now we carefully measured the effect of electric field strength on the motion of these oil droplets, and then Mulliken concluded that the magnitude of electrical charge Q that the droplets were containing was always an integral multiple of the electrical charge E, because these oil droplets were actually made up of atoms, and these atoms had electrons in them, and whatever value of electrical charge on these droplets we got, it was always a multiple of the charge on the electron. That is, Q is equals to Ne, where N could take any value from 1, 2, and so on. So in the chamber, the forces that were acting on the oil droplet, first of all, because the oil droplet was falling down, so it was the gravitational force, and because it was charged, so there were electrostatic forces also. So this led to the discovery of electrons, and this was the experiment carried out by Mulliken, which was the oil drop experiment that led us to find out the charge by mass ratio. Next, we will be talking about the discovery of protons and neutrons. Now, in the discovery of protons and neutrons, the electrical discharge carried out in the modified cathode ray tube led to the discovery of particles which were carrying positive charge, and these were known as canal rays or anode rays. So what was arising from the cathode were actually the cathode ray particles, which were the electrons or which behaved as electrons in the presence of electric or magnetic field. And what arose from the anode, which was there on the right hand side, are called the canal rays or anode rays, which were actually carrying positively charged particles. The nature of the positively charged particles depends on the nature of the gas that is present. As we saw, the cathode ray particles did not depend upon the nature of the gas that was present, but the anode rays are going to depend upon the nature of the gas which is present. E by m value of even the positive rays or anode rays was found to be not similar to that of the electron, and its value actually depended on the nature of the gas. Some of the positively charged particles are going to carry a charge which is in multiples of the value of E, but the behavior is going to be opposite to that of electrons in the presence of electric and magnetic field. That is, we saw that the electrons bend towards the positive pole, whereas the positive rays are going to bend towards the negative pole. The smallest and the lightest positive ion which was obtained was from the hydrogen gas, that was proton H+. Now it was found that the mass of the proton was 1.672 into 10 raised to the power minus 24 kgs, and charge was same as that of E with just a positive sign, that was 1.6 into 10 raised to the power minus 19 coulomb. So here the E by m value turned out to be 9.58 into 10 raised to the power 4 coulombs per gram, or you can also convert it into kilograms as 9.58 into 10 raised to the power 7 coulombs per kg. Or you can also write it in the instead of the SI units, you can write it in CGS units as 4.8 into 10 raised to the power minus 10 ESU by 1.672 into 10 raised to the power minus 24 grams, and it turns out to be 2.87 into 10 raised to the power 14 ESU per gram. Or per kilogram also can be written by simply dividing it by. So in the denominator, when we divide, it goes into the numerator, gets added 1000. Okay. Next was the discovery of neutrons. So we know that electrons arise from the cathode and protons arise from the anode. Now, where is the place for the rise or the birth of the neutron? Neutron was discovered by James Chadwick. You have to remember the names of the scientists who discovered electron, protons, and neutrons. Now, these were the particles which were discovered by bombarding a very thin sheet of beryllium. So, we took a very thin sheet of beryllium and we bombarded it with alpha particles, and this led to the discovery of neutrons. So, alpha particle, remember, is nothing but, what is alpha particle is something really very important for you to understand and to remember. Alpha particle is nothing but helium 2 plus ion. Okay, very simple to learn. So what happened was beryllium, which has Atomic number 4, mass number 9, that is, it has 4 electrons, 4 protons, and 5 neutrons. When it was bombarded with the alpha particle, which is 2 helium-4, 2 plus, we actually got carbon 12 along with 1 neutron. So if you carefully see, when you add these two mass numbers, 9 plus 4 is 13, and when you add these two, 4 plus 2 is 6. So 6 comes here, but when there is a 12 here, that means there is going to be a particle that is going to be released with 1 here and 0 here. And the particle which has 1 mass number, 0 atomic number, means we cannot say that this is mass number and this is atomic number. So that is actually going to represent a neutron. Okay. Similarly, when 2713 aluminium was bombarded with helium, I want you to write down the products for yourself. When there is going to be released a neutron, so this is where you get 26 here, and sorry, 27 plus 4, 31. So you get 30 here because 1 will go with the neutron. 13 plus 2, 15 here. So 30, 15 is nothing but phosphorus. This is how easy it is to predict these reactions. Okay. Now, neutrons were not deflected either by magnetic field or by electric field, indicating that they were not charged. The mass of the neutrons is found to be slightly higher than that of proton. It was found to be 1.675 into 10 raised to the power minus 24 grams, or you can write it in terms of kg. That is 1.675 into 10 raised to the power minus 27 kg, and the E by M value, because the charge is 0, therefore charge by mass ratio is going to be 0. Do remember the names of the scientists who have discovered electron, neutron, and proton. Do remember the charge and mass values of each of these 3 subatomic particles, and very importantly, do remember the charge by mass ratio also. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app for continuous learning through your smartphones. Keep learning with First Online University, a team of millions of learners and educators worldwide.